Welcome to today's lesson on Fleming's left-hand rule. In this lesson, we will introduce Fleming's left-hand rule and look at a case of applying it. Last lesson, we learned about the motor effect. We learned that the motor effect happens when a current-carrying wire is placed in a magnetic field, and this interaction of the magnetic fields creates a force that moves the wire. Okay, but how do we work out which direction the wire moves in when these magnetic fields interact? Well, that's exactly what Fleming's left-hand rule helps us to work out. So let's find out how it works. As we just mentioned, Fleming's left-hand rule shows us how to predict the directions of the force experienced by a current-carrying conductor in a magnetic field. So it provides us with a simple way to remember how a motor works. The rule states that if you align your left hand with specific fingers representing various physical quantities, you can determine the direction of the force on a conductor. To properly use Fleming's left-hand rule, arrange your thumb, first finger and second finger so they are all perpendicular to each other, forming an L shape like this. Each finger represents a specific quantity. The thumb represents the direction of the force. The first finger represents the direction of the magnetic field, pointing from north to south. The second finger represents the direction of the conventional current, which is from positive to negative. So remember, this is a useful rule to work out the direction of the force on the wire in the motor effect. The direction of the force is represented by your thumb. So the way that you would use this in practice is that you would be told the direction of the magnetic field, and you point your first finger in that direction. You are also told the direction of the conventional current, so you point your second finger in that direction. Now that we have these two pieces of information, we have everything we need to find out the direction of the force on the wire. By using Fleming's left-hand rule and making sure our thumb and fingers are each at 90 degrees to each other, we can find the direction of the force from whichever way our thumb is pointing. So, in summary, Fleming's left-hand rule works by telling us how the directions of the force, magnetic field, and current relate to each other. To remember the finger assignments, use the mnemonic FBI starting from the thumb: force, magnetic field, and current. Let's walk through a practical example step by step to solidify our understanding of this rule. Consider a scenario where a wire carries an electrical current vertically downward, represented by a dot, and the surrounding magnetic field is directed horizontally from left to right. First, use your left hand and align your first finger so it points to the right, which corresponds with the direction of the magnetic field, B. Next, position your second finger so it points into the page, representing the direction of the current 1. This setup aligns your thumb, first finger, and second finger to be mutually perpendicular to each other. Lastly, your thumb will point in the direction of the force F exerted on the wire. In this case, your thumb will point towards you, indicating the direction of the force acted upon the conductor by the magnetic field. By following these steps, you can use Fleming's left-hand rule to determine the direction of the force acting on any current-carrying conductor within a magnetic field. In today's lesson, we delved into Fleming's left-hand rule and its significance in electromagnetism. We learned how this rule helps predict the direction of the force experienced by a current-carrying conductor in a magnetic field, a fundamental concept for understanding the motor effect. By aligning the thumb, first finger, and second finger perpendicularly, we can determine the directions of force, magnetic field, and current using the mnemonic FBI: force, magnetic field, and current. Overall, mastering Fleming's left-hand rule enhances our ability to predict and utilize the behavior of current-carrying conductors in magnetic fields, essential for various electrical applications. Watch the rest of the GCSE physics course at Sophos Education.